Good evening, everyone. In the last class, we finished about the series and parallel combination of cells. So we'll be discussing one important theorem today. That's the maximum power transfer theorem, right? So we discussed about how much power we deliver to the load resistance, right? And if we have to maximize this power to deliver to the external load or resistance, then what should be the condition to deliver the maximum power to the resistance, right? That's what we call as maximum power transfer theorem, right? We know that let's suppose we have this circuit here. This is the resistance, right? This is the resistance. This is the resistance of resistance, resistor of resistance R, right? And let's suppose this is a battery of internal resistance of small r, right? And it's connected with some EMF E, right? The battery is having EMF E with internal resistance small r, and the external load connected to this system is capital R, right? And we know that whatever the power delivered across this load resistor R, it will depend upon the potential drop across this load R, that's V square over R, right? And the resistance of this load itself, right? Or we can write it as I square R, or we can also write it as V multiplied by I. Whatever the potential drop across this R resistor and the current I flowing through this resistor, that's how we calculate the power transferred or delivered to this resistor R or load R, right? Now what we want to do is that we just want to maximize this power, right? We want to maximize this power, right? So it means that if we calculate this power, right, through this load, the power will be, the current through this resistor will be, if we calculate the current, it will be I is equal to E upon R plus R, where R plus R is the total resistance for this circuit and E is the EMF for this circuit, right, supplied by this battery, right? So this will be the total current flowing through this resistor R, right? And if we calculate the power through this resistor R, it will be nothing. It will be the I square R, that will be E square upon R plus R whole square multiplied by its own resistance R, right? But multiplied by its own resistance R, right? Now what we want to do is that we just want to maximize this power, right? So here are, for different batteries, we know that for different batteries the internal resistance is different. It means that the maximum the power delivered to the external resistance resistor will also depend upon the internal resistance of a battery, right? Now to maximize this power, right? To maximize this power, the first derivative of GP over TR should be equal to 0, right? Then the power delivered to this system will be maximum, right? If we take the derivative of the system, we get the condition. Just take the derivative of the system, derivative of this equation, dp over dr, put that equal to 0. We'll get that at least we should have this internal resistance R, small r, equal to the external load resistance, capital R. And this is the condition. This is the condition at which the maximum power will be transferred or delivered by the battery to the external load resistor R, right? So this is the condition for maximum transfer of power. Condition for This is the condition for maximum transfer of power. This is the condition for maximum transfer of power, right? So in this theorem we call as maximum power transfer theory theorem, right? So it means that for any circuit, if we have to just maximize the transfer of the power, just equate the internal resistance of the battery to the external load resistor. Then in that condition, the transfer of power will be maximum, right? So let's discuss this question here. You can see in this circuit we have four resistors here in this circuit: 3 ohm, 4 ohm, 6 ohm, and 6 ohm, right? Uh, with the battery having a AMF of E, right? The question says that if power consumed by 4 watt resistance is 4 ohm resistance is 36 watt, right? This is the 4 ohm resistor, right? And the power consumed by this 4 ohm resistor is nothing. It's given as 36 watts, right? And the power consumed by 3 watt resistance is given as Okay, we have to calculate the power consumed by this 3 ohm resistance and the value of this EMF E and the total power consumed in the circuit, right? Total power consumed in the circuit. So here in this, for this 4 ohm resistor, the power consumed is 36 volt, 36 watt, right? 36 watt, right? So in this question, we have to find the power consumed by this 3 ohm resistance and value of EMF and the total power consumed in this circuit, right? So power here consumed by this 4 ohm resistor is 36 watts, right? 36 watt is the power consumed by this 4 ohm resistor, right? If we calculate the potential drop across this 4 ohm resistance, that will be, we can just write this power is equal to V square over R, right? So V square should be equal to 36 multiplied by the 4, right? So it means that we will get the value of V as under root of 36 multiplied by the 4, and it has to be equal to 6 multiplied by 2, that's 12 volt, right? So the potential drop or the voltage across this 4 ohm resistor is actually 12 volt, right? And we know that the combination of the 6 ohm and the 6 ohm resistors here actually are in parallel with the 4 ohm resistor, right? So we can just write these two resistors, 6 ohm plus 6 ohm, these are in series, right? We can just replace it with 12 ohm resistor, right? So we can just rewrite the circuit like this. So it will be 4 ohm here, right? It will be 12 ohm here, right? We have just written the equivalent of these two resistors, that is 12 ohm here and 4 ohm here. And this is the 3 ohm resistor. And we are connecting it with the external battery of EMF E, right? Right. So the potential drop across this 4 ohm resistor is 12 volt, and the same should be the potential drop across this 12 ohm resistor also. It means the potential drop across this 12 ohm resistor will also be equal to 12 volts, right? 12 volts. If the potential drop across this 12 ohm resistor is 12 volts, it means that the current through this resistor has to be 1 ampere, right? The current through this resistor is 1 ampere, and the potential drop across this 4 ohm resistor is 12 volts. So the current through this resistor will be 3 ampere. It means the total supply at this junction has to be 4 amperes, right? Because whatever the current is entering the junction, the same amount of current must leave the junction, right? So as to conserve the total charge, right? So 4 ampere should be the current here, right? So 4 ampere is the actual current flowing through the 3 ohm resistor, right? So we have to calculate the power consumed by this 3 ohm resistor. So the power consumed by this 3 ohm resistor, we can just write it as I square R, right? And the current through this 3 ohm resistor comes out to be 4 amperes. It will be 4 square multiplied with the resistance 3. That's 16 multiplied by 3. That's nothing. That's equal to 48 watts, right? So 48 watts is the power consumed by this 3 ohm resistor, right? Now we have to calculate the value of E, right? Value of E. If we calculate the total power consumed, right? If we can just write this circuit now equivalently equal to, you can see that this 12 ohm and 4 ohm resistor are parallel to each other. Their equivalent will be nothing. 12 multiplied by 4 upon 16, right? That will be equal to 3 ohms, right? We can just replace these two resistors with 3 ohm, single 3 ohm resistor now. So it is 3 ohm here. It's once again 3 ohm here now, and this is the EMF of the battery E, right? This is 3 ohm and this is 3 ohm, right? So overall, this the equivalent resistance of this circuit has to be equal to 6 ohm, right? 6 ohm will be the overall equivalent resistance for this circuit, right? This is the 6 ohm, right? So 6 ohm will be the total resistance of this 6 ohm will be the total resistance for this circuit, right? And the EMF E is the EMF of this battery, right? So we have to actually calculate the total consumed power, right? We can just add, we can either calculate the total consumed power for this circuit, either we can calculate it by calculating the power consumed by each and every element of resistor here in the circuit, and adding all those powers will be the total power consumed. Or we can just calculate the total power consumed from this equivalent circuit also, right? But we know the total power of each and every resistor here. The power consumed by this 3 ohm resistor is 48 watts. The power consumed by this 4 ohm resistance is 36 watts, right? And the power consumed by this 12 ohm resistor is actually it's actually 12 watts, right? So 12 ohm resistor consumes 12 watts power, right? Consumes 12 watts power. So it means the total power consumed by this circuit has to be now equal to 48 plus 12 plus 36, right? So it will be equal to 96 watts, right? 96 watt. And same should be the total power consumed by this equivalent circuit, right? By this equivalent circuit, where the current flowing actually is 4 amperes, right? Same should be the power consumed by this equivalent circuit as well, right? So we can write this, we can actually write this equal to E square upon R, right? E square upon R, right? From here we can just calculate E. E will be nothing. The value of R is the equivalent resistance, that's 6 ohm, right? It will be 96 multiplied by 6. Under root of this will give us the total AMF of this battery, right? So we calculated power consumed by 3 ohm resistor. We calculated the total power consumed in the circuit, and we also calculated the AMF of this battery E, right? So let's move on to the next question. Applications to electric bulbs and heaters. So one of the important applications with respect to the electric power is with respect to the arrangement of bulbs or heaters, right? We have two arrangements of the bulbs. One arrangement is the series arrangement, another arrangement is the parallel arrangement, right? So we do different arrangements for the bulbs in order to maximize the glow of the bulbs, or maximize the power consumption of the bulb, so that there will be maximum brightness for a particular bulb, right? That's the purpose of this concept, right? Or the applications of the power consumed, right? So we know there are mainly two combinations. One is the series combination, another is the parallel combination, right? And in series combination, we know that in case of series combination, the total resistance is nothing. It's the sum of the individual resistances, right? Sum of the individual resistances, right? Let me just replace these resistors with bulbs here, right? So let me just draw the bulbs here, right? This is the bulb one, and this is another bulb, right? So bulb is must be having some resistance as well, right? And this is the total external supplied voltage, right? There are two things with respect to the bulb, right? There is always some specified information on the surface on the bulb mentioned in the bulb, right? One is the power consumption, right? Another is the voltage, right? These two things are always written on a bulb, right? Actually, what these two things are, these are actually what we call a specified power, or we call it as specified voltage, right? What does it mean, specified power or specified voltage, right? It means that it does not mean that when these two, it does not mean that when the bulb with the specified power actually is connected to the circuit, actually will consume that amount of power, right? It may either maximum consume that amount of power, or it may consume the less than the specified amount of power, right? So it means that specified voltage, it means that it's the maximum voltage up to which this bulb is going to work for you, right? If you increase the voltage beyond the specified voltage, which is mentioned on the bulb itself, then the bulb is not going to work, it's going to fuse, right? So similarly, specified power is the maximum output power consumption, right? That will be given by a particular bulb, right? It's not always possible that it will give the same amount of consumption, right? Most of the times, it always gives the less consumption than the specified power, right? So specified power and specified voltage are actually the voltage which are mentioned on the bulb itself. That's the maximum power it can consume, and that's the maximum voltage up to which it can work, right? But the information is very important for us, because this specified power and the specified voltage which is mentioned on the bulb itself actually will help us to calculate the resistance of a bulb, right? It will help us to calculate the resistance of a bulb, right? So I will just denote this specified power with PS and this specified voltage with VS. So for any bulb, to calculate the resistance using the specified power and specified voltage, it will be equal to Vs square upon P, right? And we know that resistance of a bulb is not going to change whether you calculate the resistance of a bulb using the power consumption, right, or the voltage across the bulb, or whether you calculate the uh, resistance of a bulb using the specified voltage or specified power. Both the things will give you the same result, because the resistance of a bulb is not going to change. So it means that the specified voltage and specified power has an important application here, that it gives us the information about the resistance of a bulb, right? It gives us the information about the resistance of a bulb. So sometimes it's not possible that the it will consume the same power. Let's suppose the power consumed by this bulb is PC. I will just denote PC with the consumed power, and V is the potential drop across it, right? So let me denote that with VC. So this R will also be equal to VC square upon PC, or we can say that V square upon PS will be equal to VC square upon PC, right? So these two are always equal, because the resistance of a bulb is not going to change, right? And one more important point about the series combination of the bulb is that we know that in a series circuit, right, when the two or more than two electrical elements are in series, they actually the same amount of current is flowing through them. If the same amount of current is flowing through them, we know the power consumption, we can write it as I square R, right? I square R, right? If the power consumption is equal to I square R, and I is constant for the series combination of the bulbs, right? I is constant because the same amount of current will be flowing. It means that the power consumption in that case will be directly proportional to the resistance of that bulb itself, right? Oh, power consumption will be directly proportional to the resistance of that bulb itself, right? It means that the bulb which is placed in a series will consume more power, or it will grow brighter and brighter if the resistance of that bulb is more, right? So it will be proportional to the resistance of the bulb. And similarly, if we have two or more than two bulbs uh, in parallel, right? If we have two or more than two bulbs in parallel to each other, right, placed parallel to each other, so what we can do is that, let's suppose that we are placing two or more than two bulbs in parallel to each other, right? Let's suppose these are the two bulbs parallel to each other, right? If the two bulbs are parallel to each other, then the potential drops across these two bulbs will be same, right? If the potential drop is same, then the power consumed, we know that it's equal to V square upon R, right? V is constant for the parallel bulbs, right? Constant. It means that the power consumption in case of parallel combination of the bulbs will be actually inversely proportional to the resistance of that bulb, right? The bulb with lesser resistance will actually consume more power, right? And the bulb with higher resistance is going to consume less power, right? So it means that if you want to, if we want to, if we want to actually maximize the output of a bulb, right? Maximize the output of the bulb with higher resistance. Put that bulb in a series combination rather than parallel combination. If you put that bulb in a parallel combination, it's going to glow less as compared to the bulb which is of lower resistor, right? So in parallel combination, I always try to put lower bulb resistors there, right? So as to maximize the output of the brightness, right? So these are the two important things with respect to the combination or arrangement of the bulbs in series and parallel, how the consumption of the power takes place, right? So we have a question there here on the screen. Let's try to discuss this question first, right? Then we'll move further. The question is a coil boil some amount of water in 20 minutes, right? There is a coil, right, which boils some amount of water in 20 minutes, right? Now this coil is cut into two equal parts and these are connected in parallel. Then find time taken by this combination to boil same amount of water, right? That means that you can see that this was initially the resistance of this coil, right? This was the resistance of this coil, right? Then the heat produced in this coil will be nothing. It will be I square R multiplied by T, right? I square R multiplied by T, or we can just write it as V square over R multiplied by T. So this will be the heat produced in this heater, right? When the resistance was R. Now what we are doing that we are just cut this coil into two equal parts. We know that resistance of a conductor is nothing. It's proportional to the length of the conductor, right? It's proportional to the length of the conductor. It means that if we cut a conductor into two equal parts, then the resistance is also going to get halved, right? So it will be half, right? So the new resistance R dash will be actually R upon 2, right? Now it means that now these two pieces are actually now put parallel to each other, right? These two pieces are now put parallel to each other. So it will be R upon 2 here, right? Now we have to see what will be the heat consumption, right? What will be the heat consumption by this circuit, right? We know that in parallels, once again, the potential drop will be the same. That will be equal to V, right? That will be equal to V. And the heat consumed here in 20 minutes will be V square upon R, right? We can just replace this 20 minutes. Let's calculate it in hours, right? Or let's put it as it is. That's the 20 minutes, right? So R upon 2, right? V is the potential drop, right? Let's suppose H dash is the new heat, right? Now H dash is the new heat, right? So it will be once again V square upon R equivalent. If we calculate the R equivalent of this circuit, R equivalent of this combination, it will be R upon 4, right? It will be R upon 4. So V square upon R multiplied by 4, right? V square upon R multiplied by 4 and multiplied by this time T dash, right? Now, in order to boil this water, it will actually consume now the same amount of heat, right? It will consume the same amount of heat because the boiling temperature of the water is fixed. So at particular consumption of heat, right, a particular amount of consumption, the water is going to boil. So it is not going to change, right? But the only thing here will change is that the time it will take to boil the water, right? So it means that the heat consumption should be same. We can just put this heat consumption equal to V square upon R multiplied by this 20, right? So V square upon R, V square upon R will get cancelled. So T dash will be nothing. It will be 20 upon 4, right? That will be equal to 5, right? 5 minutes. So it means that in case of parallel combination, right? Parallel combination, it will just take 5 minutes to boil this water, right? It will just take 5 minutes to boil this same amount of water, right? So the answer to this question is 5 minutes. So two bulbs of specifications, right? 25 watt and 100 volt. And then we have another bulb of 100 watt and 100 volt. So it's actually mentioned here, these are the specifications of a bulb. By specifications of bulb, we mean that it's the specified power and the specified voltage, right? They are connected in series to a source of 100 volt, right? Then we have to find a resistance of each bulb, power consumed by each bulb, right? Which bulb will have more brightness, right? So all these things will be calculating one by one, right? So let's discuss part one. That's the resistance of each bulb, right? Resistance of each bulb. So power consumption of the first bulb is, that's the specified power, that's 25 watts, and the specified voltage is 100 volt, right? Then the resistance will be nothing. It will be equal to resistance will be equal to V upon the specified power, right? Specified voltage square upon the specified power, right? We know that power is nothing, it's V square upon R, right? So it means that the resistance will be specified voltage upon the specified power, and the specified voltage is 100. It will be 100 square upon 25, right? So we can actually write it as 100 upon 25 multiplied by 100, right? So it will be 4 multiplied by 100. It's the 400 ohm, right? So it means the resistance for this 25 watt bulb will be 400 ohm, and similarly for 100 watt bulb, resistance has to be equal to, it will be 100 multiplied by 100 upon 100, right? That's equal to 100 ohms, right? So the resistance of each bulb is actually 400 ohm of the first bulb and the 100 ohm for the second bulb, right? So this is the part first. Let's move on to the part second, that the power consumed by each bulb. Power consumed by each bulb. So these are actually placed in series, right? These bulbs are actually placed in series, right? One of 100 ohm, another of 400 ohm, right? Right? And they're connected to a 100 volt, right? So the power consumed will be nothing, whatever be the current flowing through this circuit, right? Whatever be the current flowing through this circuit, it will be the same current flowing through 100 ohm and the 400 ohm resistor, right? So the equivalent resistance for this circuit will be nothing. It will be equal to 500 ohm, right? Or the current I will be nothing. It will be equal to 100 upon 500. That's equal to 1 by 5 amperes, right? So the current I has got value 1 upon 5 amperes, right? So I is equal to 1 upon 5 amperes, right? This is the value of the current, right? The power consumption by 100 watt bulb will be P100. That's equal to I square R. That's 1 upon 5 square multiplied by 100, right? That will be equal to 100 upon 25. That's equal to 4, right? It means 4 watts. Now you can see clearly that here the specified power is different than the consumed power. So it's not always like that. The whatever the power is specified on a bulb, it is the same amount of power it's going to consume. No, it's not always like that. So the specified power here mentioned for this bulb was 25 watts, but the power actually it consumes is 4 watts only, right? So similarly for P, that's P25, right? That's for P25. And for P100, the resistance is 100 ohm, right? Let me just write it as P1 and P2, right? So for 400 ohm, it will be 400 multiplied by 1 upon 25, right? That will be 400 upon 25, right? It will be actually 16 watts, right? The power consumed by the 400 ohm bulb will be 16 watts, and the power consumed by 100 watt bulb will be 4 watts. Now, question is that uh, which bulb will have more brightness? It's obvious that the bulb which consumes more power, right, will have more brightness, or we can say the bulb with higher resistance is going to have more brightness. So 400 ohm bulb will actually produce more brightness. So it means that it will glow more, right? It will glow more. So 400 ohm bulb will actually glow more. So 400 ohm bulb is going to glow more, right? If in previous question 100 volt source is replaced by 300 volt source, then which bulb get fused, right? It's a very good question, right? Now the question is that which bulb is going to get fused uh, when we replace 100 volt bulb by the 300 volt 100 volt battery with a 300 volt battery. So let's suppose if we are replacing battery of 100 volt with 300 volt battery, right? This is the 300 volt battery here. This is the 300 volt battery here. So this is the 100 ohm resistor bulb. This is the 400 ohm resistor bulb, right? So it means that let's suppose I current is flowing through this circuit, right? Let's suppose I current is flowing through this circuit. Now this I is nothing. It will be equal to 300 upon 500, right? So it will be 3 upon 5 amperes, right? 3 upon 5 amperes. 3 upon 5 amperes. So if we calculate the potential drop across this bulb, 100 ohm bulb, let me call that as V1. That will be current flowing through this bulb. That's 3 upon 5 multiplied with the resistance. So this is actually 3 multiplied by 20, right? That's equal to 60 volt, right? 60 volt. So V1 is 60 volt, then V2 is nothing. It's actually equal to 240 volts, right? 240 volts. So it means that the potential drop across across the bulb which is of 400 ohm, right? Resistance of 400 ohm. It means 25 watt bulb, right? 25 watt bulb. The potential difference is actually greater than the specified voltage, and we already know that whenever the potential is greater than the specified voltage, right, then that bulb is actually going to fuse, right? It means that the 25 watt bulb will fuse here, right? 25 watt bulb is actually going to fuse, right? Will fuse. Reason is that because the voltage across this 25 watt bulb is actually greater than the specified voltage, right? So it will actually fuse when the bulb will fuse. One of the bulbs will fuse here in the circuit. It means that actually no current will be flowing through these bulbs because 100 ohm bulb is actually fused. When 100 ohm bulb is fused, then the current through the circuit has to be zero, right? So there will be no current through the circuit, or we can say there will be no power consumption at all in this situation, right? In this situation, there will be no power consumption. Now let's move on to the important devices that we use in our labs also, right? The two, three important devices are, one is galvanometer, another is ammeter, and the third one is the voltmeter, right? So we know that ammeter and galvanometer are the two very important devices with respect to the measurement of the current, right? Ammeter is used to measure the current through a circuit, right? And one more important point about the ammeter is that it's always connected in series, right? It's always connected in series, right? So ideally speaking, that ammeter should have zero resistance actually, right? So that it will measure measure the maximum. It will measure the current flowing through it with the great accuracy or the maximum accuracy. But that's not the situation actually. There is always some resistance associated with the ammeter itself, right? Because of that resistance, some current is flowing through, will definitely flow through the ammeter, and there will be some potential consumption, right? Potential drop consumption by this ammeter. Because of that, the ammeter will not actually measure the current with accuracy, right? So to measure the current with accuracy, we should have an ammeter of zero resistance, because so that the potential drop across that ammeter will be zero, right? So ammeter actually is used. It's a very less sensitive device, right? It's actually used to measure a good amount of current, right? Like if we have to measure 1 ampere, 2 ampere, 3 ampere, 4 ampere currents, then the device will be using will be the ammeter, right? But the thing is, why do we need galvanometer, right? The important property about the galvanometer is that its sensitivity, right? Its sensitivity. It's very sensitive device with respect to the external current, right? It sensitivity by sensitive we mean that for a very small of current, it actually shows the huge deflections, right? For a very small amount of current, like the current, if the current is even in the range of microamperes, milliamperes, right? 2 microamperes, 3 microamperes, 5 microamperes, then this galvanometer is still going to show some deflection to detect the current, right? So actually, the galvanometer is the device which is used to detect the presence of a current in a circuit, right? So whenever we have to check whether in a circuit there is a small amount of current, right? There is some current present in the circuit, then it's the galvanometer will be using for that, right? Because it's a very high sensitive device. For very small amount of current, it will show actually a huge deflection, so that we can actually detect a current in a circuit, right? So sensitivity of this galvanometer is actually defined by the deflection per unit current. That's the current sensitivity, and the voltage sensitivity we define as the deflection per unit voltage, right? So that's the reason whenever we have small amounts of a current in a circuit, we use galvanometer, right? And it's the same galvanometer which is used to construct ammeter and voltmeter as well, right? With some specifications into the galvanometer or some modification done to the galvanometer, we actually get the voltmeter and ammeter as well. Let's see what specifications, what modifications should be done on a galvanometer so as to get the ammeter and voltmeter of some specified range of measurement, right? So this is the ammeter here, right? You can see this is the ammeter and it's always connected in series, right? It actually measures a large amount of currents in amperes, right? Like 1 ampere, 2 ampere, 3 ampere. So let's see actually how we're going to convert this galvanometer into ammeter and voltmeter, right? So how actually we try to convert ammeter galvanometer into ammeter. We know that we just want to increase the accuracy of ammeter, right? If we want to increase the accuracy of ammeter, to increase the accuracy of ammeter, we just want to reduce the resistance of a circuit, right? We want to just uh, make sure that the resistance of the overall resistance of the overall device is actually very negligible, right? So that it does not consume some voltage across it, or we can say that the accuracy of the measurement of current will increase. So to achieve this, what we do is that we just place a shunt, that's the very small resistor, right? A resistor of very small resistance parallel to this galvanometer, right? Parallel to this galvanometer. That resistance or that resistor we call as shunt resistance, right? So you can see here in this picture, S is the shunt here, right? It's nothing is the shunt, right? We have placed it parallel to the galvanometer, and there is some current approaching the galvanometer I, and some part of current flows through the galvanometer, that's IG, and the rest part of the current is going to flow through the shunt resistor, that's I minus IG. That's the remaining part of the current, right? So for ideally speaking, for ideal ammeter, the resistance should be zero, right? Resistance should be zero, but it's not. We cannot actually make the resistance of a conductor zero, right? Practically speaking, right? So it's not achievable for us to have an ideal ammeter, right? So there will be always some error in the measurement of the current by the ammeter, right? So IG is the current through the galvanometer, and I minus IG is the current through the shunt, and I is the total current, right? So it means that we can just write down it as I current has to be equal to, that will be IG, right? Plus I minus IG, right? You can see that it will be once again equal to I, right? That will be once again equal to I. So these shunt resistance and the galvanometer are parallel to each other. It means whatever the potential drop across the galvanometer will be, same will be the potential drop across the shunt resistor as well, right? So it means we can just write S multiplied by I minus IG, right? That must be equal to IG multiplied by G. What is this G? G is nothing, is the resistance of galvanometer, right? It's the resistance of galvanometer. It's the resistance of galvanometer. It's nothing, it's the resistance of galvanometer, right? But IG is nothing, is the current through, or we can say it's a range of galvanometer, right? Range of galvanometer. And what is this I? It's nothing, is the range of ammeter, right? And this S is the shunt resistance, right? So we can write this shunt like this. So S has to be equal to IG multiplied by the G, that's the resistance of galvanometer, upon I minus IG, right? Upon the I minus IG, right? Or we can write it as G upon, right? G upon, it will be I upon IG minus 1, right? Or we can write it as G upon N minus 1, where N is nothing, N is equal to I upon IG, right? I upon IG. So that's how we calculate the shunt resistance S, value of shunt resistance S, to achieve the particular range of measurement, right? For the ammeter, right? If we have given range of ammeter, right? We want to calculate this given range of ammeter into the given range of ammeter, right? Then this should be the shunt resistance, or the resistance of the shunt placed in parallel to the galvanometer, so as to achieve the given range of ammeter, right? So let's try to learn it with the help of this example, right? You can see here on the screen a galvanometer of resistance 99 ohm, right? We have a galvanometer of resistance 99 ohm, right? So it means that G is equal to 99 ohm, right? 99 ohm of range 10 milliampere. It means that galvanometer is having a range of current that's equal to 10 milliampere. So we can write it as 10 to the power minus 2 amperes, right? That's the range of galvanometer, right? Now we have to convert it into a ammeter of range 10 amperes. So it means I is the current that will be measured by this ammeter, and it should have a range of 10 amperes. So 10 amperes is the I, right? Value of I. Then find the required resistance. Required resistance is the shunt resistance, right? So the shunt we should place parallel to this galvanometer, right? That is equal to S is equal to G upon N minus 1, right? G upon N minus 1. The value of G is 99 here. And N is the nothing is the ratio of the range of ammeter current and the range of galvanometer current, right? That's 10 upon 10 to the power minus 2 minus 1, right? So it will be equal to 99 upon, so it will be 10 to the power 3 minus 1. So we can almost say that this 10 to the power 3 minus 1, or we can write it as 99 upon 999, right? So it will be 99 upon 999, right? 11 upon 111. So this will be the final shunt resistance. That's the 11 upon 111 will be the final resistance for this, right? Or we can just replace, we can say that it will be approximately equal to 99 upon 1000, right? That will be approximately equal to, it will be approximately equal to 0.099, right? That's the approximation, right? That's the approximation. That 0.099 will be the approximate value for this shunt resistance, right? So this amount of resistance, or this amount of shunt we should place parallel to this galvanometer to attain a range of a meter measurement equal to 10 amperes, right? So let's discuss another question. Resistance of galvanometer is 45 ohm, right? If only 10% of the mean current passes through the galvanometer when it is connected to a shunt, then find the shunt resistance, right? We'll just draw the circuit here. This is the shunt resistance, right? And if this is the shunt resistance, and this is the galvanometer here, right? This is the galvanometer here. Shunt resistance of resistance S, galvanometer of resistance 45 ohms, right? Right. This is the total current supply, that's I, right? If only 10% of the mean current. So only 10% of the mean current is flowing through the galvanometer. So the current through the galvanometer is actually 0.1 I, right? That's 0.1 I. And rest 0.9 I is going to flow through the shunt, right? And find the resistance, right? Then find the shunt resistance, right? We have to find the shunt resistance. And the shunt resistance will be nothing. It means 0.9 into 9I, 0.9I into S should be equal to 0.1I multiplied by 45, because these are placed in parallel to each other. They must have the same potential drops. So I and I will get cancelled. So S will be equal to, it will be 4.5 upon 0.9, right? 0.9, or we can write it as 0.91, 0.95, right? That's equal to 5 ohms. So S is equal to actually 5 ohms. So the shunt resistance placed in parallel is a resistance of 5 ohms, right? Now let's look at this, what we call as voltmeter, right? And voltmeter, we know that it's also achieved. Voltmeter is also achieved using the what we call as galvanometer, right? We convert the galvanometer into voltmeter when a high resistance is actually connected in series with the galvanometer, right? We place a high resistance in series with the galvanometer to actually convert galvanometer into voltmeter. The reason why we do so, why do we need high resistance in parallel to the in series to put series in with the galvanometer? Because we know that if we place a lower resistance, right? If we place a voltmeter of very less resistance, then it is definitely going to consume some current through it, right? And it will consume some potential drop as well, right? It means that wherever we place a voltmeter parallel to a given resistor, it will not actually calculate the same potential drop, or it will actually the potential drop measured by the voltmeter will be different, right? It will actually uh, consume some energy. It will actually consume some current flowing through it, and the potential drop across it also, right? So in order to avoid that, we just want to increase the resistance of this voltmeter, right? So that there will be no current down through the voltmeter, and it will actually measure the potential drop across the given resistor with high accuracy, right? So maximum what we can do is that, ideally speaking, that we can just make the resistance of this voltmeter equal to infinity, but that's not actually possible. That's the ideal situation, right? So for an ideal voltmeter, we should have the resistance of a voltmeter equal to infinity, right? So for that, we have to place a shunt or a resistor of infinite resistance, right? In that case, we can say that the ideal voltmeter actually will behave as an open circuit. Why? Because there will be no current flowing through it, right? Whenever no current will be flowing through, whenever no current will be flowing through it, it means that the circuit will be open circuit, right? But it will actually measure in that condition as well. It's going to measure the potential drop, right? So ideally speaking, it will be an open circuit, right? But that's not possible. But we still have to make a voltmeter uh, of high resistance, right, to increase the accuracy, right? So you can see the current I is actually flowing through this circuit, right? This is the main current I, right? And it is the main current I, right? Then the current Ig will be flowing through this galvanometer, right? G, and H is the resistance that we have placed in series with this galvanometer. The potential drop across the galvanometer will be Ig multiplied by G, right? Uh, let me just call the potential drop across this shunt across this resistor as Vs, right? Vs or Vh, whatever you call it, right? And that has to be equal to the potential difference between these 2 points A and B. Let me call that equal to V, right? Let me call that equal to V, right? So that's equal to V, right? So Ig plus Vs is equal to V, right? So from here we can write the value of Ig, that will be equal to V minus Vs upon the G, where G is the galvanometer resistance, right? Galvanometer resistance. And what is the V here? V is actually this V is nothing, it's actually the range of voltmeter, right? Range of voltmeter, right? For IgG, we can just replace Ig comes out to be V minus Vs upon G. We can replace this Ig with potential drop measured by the galvanometer, that's Vg upon the resistance G, right? Resistance G. That's equal to V minus Vs upon G, right? Or Vg will be equal to V minus Vs. What is this Vg? It's the range of Vg is nothing, is the range of galvanometer, right? So using this equation, we can actually calculate the range of voltmeter, right? Or we can also calculate the Ig, right? Current through the galvanometer to actually attain a particular range of voltmeter, right? So that was it with respect to the voltmeter conversion. We'll be doing some questions in the next class with respect to the voltmeter also, right? So let's stop here. We'll be meeting the next lecture. Till then, take care and goodbye.